desirable. I'm just telling you. Um, so today we're looking at linearizing data and then deriving a, a formula based on that linearization. So the first thing you need to do is just write yourself oops, some information from here. And we've already talked about the correlation coefficient, and it's actually calculated by the linear regression equation. And so if the data is not linear, which is all of these things that we've been doing, that correlation coefficient can't be calculated unless the data is linear. Maybe you remember, didn't we have one yesterday that looked very different, but the correlation coefficient was the same? Do you remember that? And somebody questioned that. But what we do is we take our data that is not linear and we do something to transform it so that it makes a line. We're going to linearize the data. That is transforming it so that it appears to cluster about a line. And this is called linearization. And to linearize the data, we either change the X list or the Y list, or sometimes we'll change both of them, okay? And there are four or five different ways to do this. I'm going to tell you that in class today, I'm going to go over two of them, and on the homework, you could have any of the five, but on quizzes and tests, I'll only be testing you or quizzing you on the two that we go over in class. Does anybody need to see this? Whatever I've underlined, that's what you should be writing as we go. And then I'd like you to be able to see this. So I don't think you necessarily have to write these graphs, but maybe you just want that the original data kind of looks like this, and that so you're going to write the original data kind of looks like that, but then when you linearize this data, it looks like that. It looks more like it is in a straight line. And of course, the book authors are picking things that kind of look almost perfect. If you look at these two sets of data, do you notice that in this case, and that's not always the case, but in this case, the X list goes from 0 to 7 on both of them, right? So they didn't change X at all. But the Y list here is 1, 1.4, 1.9, a bunch of different numbers. And then the Y list on the second one is actually the ln of Y. So the ln of 1 is 0 because e to the 0 is equal to 1, kind of that whole thing. And then what happens is it made the data look like a straight line. So a lot of times you will have to decide what method to linearize the data, but I'm going to tell you also that I'll be announcing to you on the tests and quizzes which model we're going to use and linearize the data. Well, there's a bunch of rules, so that's the next thing. Okay, so there's some information here. I'll let you kind of look at that as if you're not here today. Otherwise, we'll in class be kind of going over the things we need. Okay, so these are the transformations for linearizing the data. So you need to write all of these in your notes. There's 4 of them. And on the homework, you might have to use any of the 4. I'm telling you right now that on tests and quizzes, you will have to know the exponential and the power. And those are the 2 examples we'll go over today. So for homework, you could have to do any of these. And part of the reason I'm doing that is then you don't have to memorize 4 things. It's just 2 things. Does that make sense? But for quizzes and tests, I will only ask you to linearize data for a power and exponential uh, models. So you want to know those two rules. Yes, x comma. So the quadratic function y equals ax squared plus bx plus c. The graph is going to be x comma the square root of y, and I'll explain what that means as we set up our table. The exponential is y equals a times b to the x, and when we graph it, we're going to graph x comma the ln of y. So in both of these, the x column just stays the x column, the y column changes. If it's logarithmic, y equals a ln x plus b, we would change just the x to the ln of x, comma, and y. And then the second one that you have to know is the power function, and that's y equals ax raised to the b power. And then we change the x and the y into the ln of x and the ln of y. So just to have an idea when you're doing homework, especially if it's going to map a quadratic function, the data might look like that, right? Do you agree that that looks like a quadratic? If it's going to be exponential, it could look like this, or it could look like that. Exponential decay, exponential growth. If it looks logarithmic, it might look kind of like that if it's going to look logarithmic. If it's going to be a power function, think about that b if it's even or odd. If it's even, it's kind of going to have that parabola shape. If it's odd, it's going to kind of have that shape that looks like that. So a power function, it might look like a parabola kind of thing, or it might look kind of like this, or it could even be flipped upside down. So do you agree that the quadratic and the power could be used in similar situations sometimes, but maybe not as we go? Now, the word is linearize, right? So when you hear the word linearize, you should think of a line. Do you agree? Linearize, a line. So we're going to get a linear equation. Do you remember y equals mx plus b? Yes or no? Y equals mx plus b. Okay. And so that's what kind of regression equation we're going to do, is we're going to do y equals mx plus b. But none of these graphs are linear, correct? So we have to learn something new about that. We use something called a hat. Okay? And a hat in my mind looks kind of like a caret key. And the hat means that that is not the original data. So like in this instance, for the quadratic, we use x and y are our original. And that's going to map onto x and the square root of y. So when I get a linear equation for this, that x is plain old x, right? Because I didn't change it. But the y that I'm using, I'm going to call it y hat because it's not my original y, okay? It's a different y. And I have that written, I think, down here. So it's hard for me to do that when I type, but x hat means it's an x that um, is something that's been changed, and y hat. So it's only used for the values that we've changed as we've looked at this, just to kind of let you know. Now, I'm going to go over this, and we're going to go over it in a very sequential way, and I'm going to write a lot of calculator directions, I think, as we go. We do have to do, the reason we're doing this right now in this section is we're going to have a linear equation, but then we have to change it either into a power or exponential equation as we go. So we only use the hat if we change the data as we go. You ready? Everybody have a calculator? Okay, So the first thing is just make a scatter plot of that. And I don't want to spend a lot of our time making scatter plots and things like that, but because we have just two problems to go through, but they are kind of long. So you take a minute and put that in list one and list two, correct? And then you're just going to make a scatter plot. Let's see, x maybe from 0 to 5, y maybe from 0 to 200, right? So 0 to 5, 0 to 200. Just a second to restart this. Okay, so I don't really want to spend time making scatter plots. So if that didn't work out, just look at mine right now. See the scatter plot? That's what it should look like. And we're going to say that this might look like a power model, and we're gonna make some data so that we can have that. Now, the most important thing right now is that in list one and list two, you want to have the data. Does everybody have that? In list one and list two is that data that is right there. And I'd like to take some snapshots of that, but I think I'll do that in a little bit. So the first thing I'm going to do is kind of write our directions. So put data in list one and list two. So this is list one, list two. Make scatter plot. And in this, it told us to assume a power model, so we don't have to check and see what's going to happen, but we will see that this data is linearized in a few minutes as we go. For step two, we're told to use a power model. And so what that means, and I'm going to write it this way, is xy maps onto the ln of x and the ln of y. And where did I get that? Right from my notes, right? Everybody agree? I just got that from my notes. Now, I don't remember if we did this before, so I'm going to tell you I have list one and list two. Let me see if that, oh good. I'm going to slide that over just a little bit because I want to get list 3 is going to be the ln of x and list 4 is going to be the ln of y. I'm going to explain how to do it, so maybe don't do it immediately, and then we'll do this. So what you want to do is you want to make step 3. Well, that's just finding them out. Yep, we'll make list 3 equal the ln of x, and so that's going to be the ln of, where's x, list 1, and then we're going to make, and then that's going to be x hat is list 3, okay? And then we're going to make list 4 into the ln of y because I needed both of them, right? I'm transforming both sets of data. And that's going to be the ln of the y list, which is list 2. And that's going to be y hat. So right here, before I move on, I'm going to say that's going to be list 3. Oops. And this is going to be list 4. This is the ln of x and the ln of y. Okay, now, do you know how to easily make it dump all those ln's in at once? Give me a head nod because I don't know if you know that. No? Okay, hang on. I'm just going to show everybody. Are you ready? What? Oh, my bad. So wait. I accidentally wrote too many Y's there. Sorry about that. Okay, now I'm going to the calculator. So here's what I'm going to do. I'm going to arrow over to list 3. And look, Do you see where I am? Do you see where I am? Top of list 3. So when I'm at the top of list 3, way down at the bottom, it says L3, and I want the LN, so I'm gonna type LN, and I want it to be the LN of list 1. So list 1 is, look, right there, correct? Can you find it? And so I'm gonna go second 1. I'm gonna do good math, and I'm gonna close the parenthesis, and I'm gonna press enter, boom, dumps them all in there. Okay, hang on a second. So go to the top of list 4. Okay, are you at the top of list 4? Okay, and now you're gonna go, we need that to be the ln of y. So you're gonna go ln, and that's the list 2, second 2, close the parenthesis, and there it is. The log base e. ln stands for the log base e. Now, look, I transform both x and y so that I can see what that's going to do. Just for this one, maybe for the other one if we have time, I'm going to go second y equals up to stat plot. I'm going to leave plot 1 as it is. I'm going to arrow down to plot 2. I'm going to turn it on, but I'm going to use list 3 and list 4. So second 3 and second 4. Now, one thing I'm going to say about this, do you remember those numbers were a lot littler now, correct? In these lists. So maybe I'll go look at those lists again really quick. So these only go to like 0.69 to 1.4 and negative 0.96 to 5. So can you see them on mine there? If I look at this graph, I can barely see the red ones. So if I just want to see those, I forgot kind of what they went, but 0 to 2 maybe? Is that going to be enough? And 0 to 2? No, 0 to 6. And I'm not going to see my original, but ooh, those should look kind of lined up. Do you agree? And yes, one of mine is kind of seeming off. But, and I should have gone back to some negatives. Negative 3 and negative 3. Not sure why that one is there, but do you agree that most of those red ones look? Oh yes, that one. Yeah. So do you agree that those look like they are in a line pretty much? The red. That was the original data. So we just can't see it. Just something that would fit on the graph. I'm not that interested in the graph. I want to be able to find this. So, okay, that by doing this process, this makes the data linearized. Do you agree that it pretty much looks like it's in a straight line? Now, the question that was asked is, why did I take the ln? Because I was told in the problem to use a power function, and when I use the power function, I transform the x's to the ln of x and the y's to the ln of y's because that makes it linear. If I had used one of these other ones, the data wouldn't have lined up as well as it did in this case. And like I told you, I was told to use a power model. Now, the next thing I'm going to do is for step 4, Now that that data is linearized, I'm going to find the linear regression. And since I changed both of those, I'm going to use list 3 and list 4. And we're used to doing regression equations always with list 1 and list 2. So we have to change that as we go. So I have to find linear regression. And I'm going to use number 4, which is linear regression ax plus b. And that LIN means linear, not, um, not logarithm of. And listen, the reason I'm using list 3 and 4 is I changed both the x and the y. If I had only changed one of them, I would use the original that stayed the same and the one that changed. And we'll do that in the next problem of list 3 and list 4. If your calculator is older, I think you have to put commas and those lists in it. If it's newer like this one, I think you just kind of find the linear regression. So look at this. I'm going to go second quit. So I'm back to the home screen. I'm going to push stat over to calculate. I told you to choose number 4. If it looks like this, you're going to now change this to second 3 for list 3 and second 4 for list 4. And then when we calculate it, this is what we're going to get. Just tell me if you got the same thing I have on the screen. Oh, I have an error way back here because I agree with you actually. Do I have an error in my numbers? I do. I feel like that one that was kind of funny, 10.1, right? Okay, now notice it did not automatically change my list 4. So I just have to go to the top of list 4 and retype that in. So I changed my list 2. The ln of list 2, I'm just correcting an error I had there, I think. Is that better? Okay, and now I'll just go through that process again. So I'm going to push stat, calculate, linear regression. Oops, just kidding. I didn't do that right. Clear. So stat over to calculate. Number 4 is that linear regression. List 3 and list 4. Is mine better now? Okay, there's my regression equation. If yours didn't work out, you might have had an error like me. Otherwise, we'll try to go through problems, but just write things down as we go. And if you have an older calculator, when you do this linear regression and you choose that number 4, this is for an older calculator, it'll say linear regression or something, and you have to go comma, list 3, comma, list 4, and then enter in order to get the regression equations. I think if it's an older calculator, you might have to do that. So now I want to say this. These are x hat and y hat, right? Because we changed both of them. Do you agree? X hat and y hat. So um, tell me what that was. Y hat is, what was the slope? Let's make it easy. 3, right? 3x hat plus, I'll go one decimal place, 1.1 maybe? Oh no, that's what's on my calculator. Okay, yep. Oh, whoa, 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 whoa. No, no, look. Y equals ax plus b. So y equals 3x plus 1.1. Yep, I don't know. We're, as long as you have this, that's what we're, yeah, because that's the correlation coefficient R. And Colin, did you get a linear equation, but it was just a little different? Okay, and we can look at your calculator later, but right now now we're gonna do the kind of math part. So does everybody understand what is happening so far? And, okay, so we put our list one and list two in, right? We made list three and list four, the ln of list one and the ln of list two, excuse me, right? Then that should have been linearized, and it was. It looked like a line. And then we did the linear regression, because that's how you get the linear regression. And I guess, Taylor, yours had an R value. What was the R value? R. Right. So 0.99999 is the R value. That means it's very, very good, right? So now, because we changed the X and the Y, we have to put these hats on there, right? Because the hat means I changed the Y. This is not my original Y. Did I use my original Y? No, I used list three or list four. And this is not my original X data. No, I used that transform data. So once I get that linear equation, now we're going to do the math of this. And so once I have the linear regression equation, I'm going to change it back to what it was. So what did x hat stand for? The ln of the original x, do you agree? And what did y hat stand for? The ln of the original y. So we're going to change it to the ln of y equals 3 ln x plus 1.1. Now, that's our original equation with our original data. We changed it to linearize to get this, and now we have this. So our next job is to make this into something without ln's, and we want y equals. And we want it to be a power model. Y equals a times b to ax to the b power. So we're going to now do things we did earlier in the chapter sections, and we're going to exponentiate this. I'm going to make that into an exponent, and I'm going to make that into an exponent. What is the base of ln? E. So I'm going to raise each of these to using e as the base. E to the ln y equals e to the 3 ln x plus 1.1. Now, e to the ln y, what is e to the ln y equal to? Y. It's equal to y. E raised to the log base e of y is just equal to y. That's a property we had in this lesson. Now, next thing, are you getting all this? Are you understanding all this? So the next thing I just want to remind you of is this. So without looking at that problem a minute, I'm just going to remind you of some old work, okay? If you have x to the 5 plus 2, do you agree that's the same as x to the 5th times x to the 2? Do you agree with that? Just an old problem. Do you all agree with that? This is, so because this is x, 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 and that's x, x. So I get x to the 7th, right? And this is x to the 5 plus 2, or x to the 7th, right? And so they're the same thing. Okay, so we're used to seeing that with numbers, but somehow it can mess us up a little bit here. So if I have e, so maybe I'll just write over this. If I have e to the 3 ln x plus 1.1, I can call that e to the 3 ln x times e to the 1.1, and I'm doing the exact same thing. An old problem that we just reviewed. Oh, wait. No, 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 no. Wait, the question is, what is x to the 5th plus x squared? X to the 5th plus x squared. That's all it is. X to the 5th plus x squared. They're not like terms, yeah. So know this, and these problems will follow these rules. So we can separate this into e to the 3 ln x times e to the 1.1. That's just a property of exponents, and we've known that for a long time. Then the next thing that I can do is I can move that little 3 up there. Do you agree with that? I can move that little 3 up there. So I'm going to say y equals e to the ln x to the third times e to the 1.1. Everybody with me on that? Everybody with me on that? Okay, now here's another question. E to the ln of x to the third, what's it equal to? X to the third. E to the ln of x to the third is equal to x to the third. So then we're going to have y equals x to the third times e to the 1.1. Now we have a rule for that. We have a rule that says b to the log base b of x. What's that equal to? That equals, so e to the ln, that is log base e. So e to the log base e of x to the third is equal to x to the third. And that's one that we're learning all this, but we want to kind of remember. Now, next question I have for you is, do you agree? Sorry, my voice just kind of did a funny thing. This is x to the third. We're going to leave that x to the third, but e to the 1.1 is just a number, right? Okay, I want to know what it is, and I'm going to round it to a whole number. 3. Do you agree? 2.7 to the 1.1, it's about 3. Okay, yeah, yep, I'm just going to round it. So then if I rewrite this, I'm going to write it as y equals 3x to the third. Do you agree? Now, I changed that window, and I don't want to spend a lot of time doing this because I want to do the math on the next one, right? I don't care as much about the scatter plot. You can all do that. But I'm going to go to y equals, what did we just say it is? 3x to the third? 3x to the third. And I'm going to go back to my original window. I don't remember what it was. 0 to maybe 5 by 1. 0 to 200. Thank you. And I've still got those red ones. I don't care about those. But look, does that match well? It matches very well. Okay, it's a process. I understand. But we're going to do the next problem, and we're going to forego some of the graphing. So Colin, you're going to pick back up on this, and we're going to make your calculator work on this one. Okay, are you ready? Here's our next one. I'm not using a calculator, so you have to kind of be ready. So write down this table, and This is going to be, I feel like it's a little too big for me there. Okay, wait, this is going to be list one, this is going to be list two, and this is exponential. So you take a minute, put those in list one and list two. Record again. So you should have these in list one and list two, correct? And it tells us to use an exponential model. I'm not writing all those steps, but I just wrote that these are list one and list two. So this one is an exponential model, exp model. So that maps xy onto, what does it map it onto? X, ln, y. So do I need list 3 and list 4? No, I only need one, and I'm going to make it list 3, and it's going to be the ln of which list? List 2. So list 3 is going to be the ln of list 2. And I just have this number, it's 5.737. Somebody has to tell me if that's what they got. Colin, do you have list one and list two in there? For that one right there. Okay, so you're on track with your calculator. Perfect. Go to the top of list three and make it the ln of list two. So I'm going to do what kind of regression again? Always linear. Number 4, right? Say it again. Because I linearized the data, so it's going to be linear. Say it again. Right, we're always doing linear. So linear regression, I'll write that in words. Number 4 it is, right? Now, what list do we tell it to use? Using list 1 and list 3. So this is x and the ln of y. Do you agree? Because it's x and the ln of y. Someplace. Where you were. Oh, okay. Wait. Nope. Okay. You're gonna push the buttons, but so go stat. Over to calculate. Number 4. Or enter. Yep. And now you're gonna go second 1, comma, second 3. Okay. All right. Yep. I knew we'd get it. Now, okay. All right. So now x is just x, right? But y is what? Y hat. Good job. So our linear regression equation, y hat equals, what is the slope? I just want a whole number. What is it? 1. So y equals 1. Is it x or x hat? Just x. And what's the y-intercept? I did 2 decimal places. 1 point plus 1.74. Did everybody get that? Because that's the one we transformed. Y is y hat because it's the one we changed. We only changed y, not x, because of the rule they told us to use. Okay, wait a minute. I don't want to. Okay, yep. Um, oh, did you do the regression equation? Great, I know, but then we did the linear regression. Okay, now I want to finish this up. Are we this far? So I'm going to change y hat into what? lny equals x plus 1.74. Do you agree? Okay, now really these are a little different because they're not both ln, but I go through the same process. What did I do at this point in the last one? I raised them to the e using e as a base, right? So e to the whatever and e to the whatever. So I'm going to say e to the ln y equals e to the x plus 1.74. Now, e to the ln y, what's it equal to? Y. Do you agree? And now, because now this should seem like it's going to be a little easier because we're a little more familiar with it. So now if I have e to the this plus this, I can separate it into e to the x times e to the 1.74. Do you agree? Yep. Yes, Colin. Okay, right there, I have this, right? Okay, I intentionally, because the base of that logarithm is e, I'm gonna see how I did it kind of in blue. Gonna use e as the base and then raise each of those to to that exponent because they're still equal that way. Say that again. Yes, hang on a second. Y equals e to the x times, I'll just take 5.7. And then I just would rewrite it a little different, right? So y equals 5.7 e to the x. And okay, I didn't graph any of this, but if you put this in y equals and you've graphed list 1 and list 2, it should match pretty close. Somebody could tell me if that happens. Do you see that even though the problems are different, the process is pretty the same? Okay, I'm going to revisit the process, okay? So we put the original data in list 1 and list 2, right? Got it? Then then we have to figure out what we're going to be using. In this case, it was exponential. So we only had to change one of the lists, right? And if if you're asked to do those other models in homework, you might have to change just the X list, or you might change it to something different, right? But we're focusing on these in our notes. Then once you have the transform data, you do always what regression? Always linear regression, and it's the two lists you need. In this case, list 1, because the x stayed x, and list 3. List 1 and list 3. In the first one, it was like list 3 and list 4, right? Because we changed both of them. And then when you get the linear regression, you use the what's? Hats. And sometimes on both, sometimes on just one, right? And then what do you do with the hat? You change it to whatever it is, ln, and there's one that's like you change it to the square root of whatever. And then we exponentiated, right? Why did we use e as the base? Because the ln of y has, right. Then we get just y here, right? And look, did every time we get something that was added and we separated it into multiplication, right? And then something is a number. And in the other, this one is e to the x. In the other one, oh, I'll go back to it. In the other one, it was e to the ln of x squared to the third, so it was x to the third, right? So there, that was a little different. There you go. Okay, I'm done with this